Good day. Today we will be discussing about our assessment in our feedback and control systems lab. The first question is, designing an automotive suspension system is an interesting and challenging control problem. When the suspension system is designed, a quarter model, one of the four wheels is used to simplify the problem to one-dimensional multiple spring damper system. A diagram of the system is shown below. This is the diagram here. As you can see, we can see the following given, which is the X1 and the W, K1, the K2, the body mass M1, the suspension mass M2, B1 and B2. The system parameters are M1 would be the body mass, which is 2,500 kilograms. M2 would be the suspension mass, which is 320 kilograms. Spring constant of the suspension system is 80,000 newtons. The spring constant of the wheels and tires are 500,000 newtons. The damping constant of suspension system is 350 newtons per square, and the damping constant of a wheel and tire is 15,020. So the system inputs are U and has the disturbance W coming from bumps of the road. The output of the system is this difference of the displacement x minus x2. The government of the equation or the systems are d squared x1 over dt, which is equals to 1 over m1, d2 over d squared over x2 over dt, which is equals to m2. So the disturbance of W is a step signal with initially a step time equal to 0. Initially value equals 0, the final value is equal to 0, the input signal is U, and it's a step signal with a step time 0, and the final value is equals to 1. Set the simulation stop time to 50 seconds. Take note also that dx1 and dt is equals to v1 and v2 is equal to dx2 over dt. So what I first did is for the first question is create a Simulink model for the suspension system and then verify its behavior via its response plot, interpreting the response plot. So from the Simulink model, let's go to our MATLAB to show you the model that I had created. So as you can see here, I had created a automotive suspension system, which is in the given we have an integrator here, we have a sum block here, and we have another integrator here. Going to the sum block over the K1, which K1 is given as the spring constant of suspension system, which is 80,000. I had managed to change the value inside of the block. So given the K, this is 1 over M1, this is 1 over M2. I had also changed the value of it. This is the B1, which is also changed. This is the K2, this is the B2, and this is the sum block going over to the K2 and B2. So this is the sum block for all of the given blocks going through the integrator. Okay, so this is the step signal. The step signal is set to 1, 0, 0, and 0 and 1 for the initial and the final value. The step time and the final value. Okay. So as you can see, this will make the signal for this system. Okay, and going through the sum block here, as you can see, this will enter K2, B2 going to the sum block here, and this will travel through across, and it will show you the output here in our scope. And if you run our output, you can see this value. As you can see, the transition is high, which is 1.56, and its low is 8.69. And I had managed to show you the bi-level measurement so that you could have a better a better knowledge for the simulation. This is what you should write in the command window so that they could access the simulation proper. Okay, so for the next question, create a feedback control mechanism for the system using the Simulink model as shown below. As you can see, we have a step signal here, a sum block here, another step signal, a gain signal, and a MUX. Here the outputs, it is x1, dx1 over dt, y1 is equals to x1 minus x2, dy1 is equals to dt, and y1 is equals to dt. To combine these signals into a vector of signals, use a multiplexer of MUX. As you can see here, this will be the multiplexer. This will combine the signals and a constant gain feedback. As you can see here, for each of outs, the value of the gain k is equal to 0.2.3 2.3 times 10 raised to 5.10, 5 times 10 raised to 3, and 0.8 times 10 raised to 6. Set the gain to do a matrix multiplication, not an element multiplication. The input x is a step input with step time. Initial value is final value, and sample time is also set to 0. While the disturbance of the final value is set to negative 0.1, this is assumed that you are commanding the automotive to stay level, but there was a hole in the road 10 centimeters. This is a problem that we will encounter earlier. So we had to plot the control response and interpret the response in terms of the control mechanism used. Okay, so as you can see here inside the subsystem, what we will use is the first system that we had made right here. So as long as you had managed to make an automotive suspension system, you can use it inside the feedback control mechanism. This will be the control of the system. So copying and pasting it inside the subsystem, as you can see inside. Okay, here is the feedback control system. As you can see here inside, if I double click it here, you can see the automotive suspension system that I had copied and pasted. Okay, so going back to the feedback control system, you can see the MUX. The step signal, it's almost the same as the figure given. This is the sum block, and this is the gain, which is noted that it has to be matrix and not element wise. Okay, connecting all of that, you will have this given value, or this given signal for the scope run. As you can see, it's different from the given automotive suspension system, the one which was given in letter A. Okay, this step signal will enter number 2, and this step signal will enter the sum block, and this will be calculated going through 1. This will enter all of the automotive control system here. Here is where the step signal will fall, and it will go through all of these sum blocks until it reaches the outputs of 1, 2, 3, 4, 5, going to the MUX, and going through the gain, and going back to the sum block. As you can see, I had inserted a scope here so you could see the output of it. So those would be all of it. So thank you so much for your time.